Alright, so I'm going to go ahead and make the video. My kids have not gone to bed yet, so you may hear a little commentary, but... Okay, so in behavior, basically with any sort of function, you're going to have... Your function is, you're looking at the ends to the left, and you're looking at the ends to the right. So, like this part, as x goes to positive infinity, it's basically on your xy coordinate plane, it's looking at this way. Like as your function is going this way, or looking to the right, what is your function doing? Whereas this one's talking about as your function goes to the left, in that direction, what is your function doing? So that part up there at the top is always going to be there no matter what function you have. And then essentially what you're doing is you're just looking at the ends, like what direction they're going. So like if I have something like this, well, on the, this one right here is the right-hand side. So on this right-hand side, my function is going to positive infinity or just infinity. I think he just uses infinity, so I'll fix that. Just positive infinity. If it's going up, it's to infinity. And this one down here is talking about the left side. So as x goes to the left, or to negative infinity, my function happens to be going up as well. So let's say if I had a different function. Let's say if we had something like that, okay? And this one again is still to the right, so as our function is going forever to the right, is our function going to positive infinity or negative? It's going up, so that's to positive infinity. And the second one, as x goes to negative infinity or to the left, our function is going down forever, so that's going to be negative infinity. Okay. Now certain functions have different kinds of properties, and you can actually tell without graphing them, but if you're unsure, just graph them and see what they look like. If you have one with an even exponent, so like x squared, or x to the fourth, or x to the sixth, or something like that, both of the ends are going to go the same direction, so it could look something like this. That was variable, sorry. Could go something like, this. If you have an even exponent, both the end arrows are going to go the same way. So they're either both going to be like positive infinity and positive infinity, or negative infinity and negative infinity. The way that you tell if they're going to positive infinity or to negative infinity, if the function is positive, so like, I don't know, x to the fourth minus 3x squared plus 2. Okay, since the front of it is positive, there's no negative number, it's going to go up. Both ends, no matter what it does in the middle, it's both going to go up. Whereas if I had a negative in front of it, so if I had negative x to the fourth, that means they're both going to go down. Both the end arrows, no matter what happens in the middle, are both going to go down. So just kind of remember, if it's an even exponent, if the highest exponent's even, they're both going to go the same direction. If it's a positive function, they're both going to go up. If it's negative, they're both going to go down. Now, if it is, if it is a odd number, sorry, I couldn't think of the word. If it's an odd number, so like the highest exponent's x to the third, or x to the fifth, or x to the seventh, etc., etc., they're going to go in opposite directions. Most of them if the front number basically in front of it is something positive, it kind of looks like a 0, sorry. So like if I had something where, like this was a 5x to the third and then something else, or like a 3x to the third, or a 2x to the seventh. If it's an odd exponent and the front number is in a positive number, they're going to start facing down. Oops, it's going to start facing down, and as it goes, it's going to go up to the right. So, for example, this first one, as my x goes to the right, this function is going to go to positive infinity. As my function goes to the left, it's going to go down. Okay, odd exponents always go in opposite directions. And if these front numbers are even, the coefficient of that, if it's even, they're going to start from the bottom, do something, and go back the other way. Even this one's going to start from the bottom, do some stuff, and then go back up. Those are always going to be the same. Now if you had negative numbers, let's get rid of some of that. If you had an odd exponent but even number, let's say, so like if I had negative 2x to the 5th, or negative 4x to the, I don't know, 3rd, okay? Those are actually going to start at the top. Sorry. They're going to start at the top, and then they're going to end up going down. So something like this, they're going to, as it goes to the right forever, it's going to go to negative infinity because it's going down. And as it goes to the left forever, it's going to go up. So that's going to be positive infinity. Okay. So just kind of remember, the highest exponent being odd means they're going to go in opposite directions. The number in front of it basically tells you whether, it's starting up high and then going low, or if it's going low and starting high. Okay. So hopefully that helps with that. Okay. Alright, so some of these log things. Now, he solves them a little different than mine, so I'm going to look at your notes as I go through this to do it the same way that he does. Not that it's any easier or harder, it's just a little different. I don't want to confuse you. Okay, so when you're trying to solve for an exponent, what you want to end up doing is you want to take the log to both sides. Okay. So when you're looking for an exponent, when your x is an exponent, you're going to end up going through and logging both sides. And once you go through and do that, okay, this kind of becomes like a log. Let me see how he does this. Oh, he pulls. Okay, so he pulls this exponent and puts it in front, so that goes x log of 2 equals a log base of 12. Okay, and then since you're solving for x, all you have to do then is just do, divide by log base 2 to both sides. And you would just type that in your calculator. So x is going to equal, in this case, log base 12 divided by log base 2. It doesn't look like a 2 very well. Alright, so same kind of thing with this one. What you're going to do is you're going to log both sides. And you're going to take that exponent and put it in the front. So this is going to end up being x log of 3 equals log of 20. And then to solve for x, all I have to do now is just divide by log of 3 to both sides. And those are gone. And so x equals whatever log of 20 divided by log of 3 is. So it looks like you're going to have some of those in your test. Okay, one of these types of logs. Alright, so what you're looking for is you want to see if your logs have the same base. And if they do, you can combine them into 1. So we're going to combine this into 1 log base 3. And what you do is these parts in the parentheses, you want to multiply them together. So when I multiply x times x and x minus 2, it's kind of like your distributive property. You're going to get x squared minus 2x equals 3. And once you get it down to one single log, you can rewrite it into exponential form. Basically what you do is you take this base, oops, sorry, I don't know why it's doing that. Take this base, darn it, it's doing something funky, sorry. Start with your base, and you're going to raise it to that exponent, and then equal it to that. It kind of makes this loop. So we get a 3 to the 3rd is equal to x squared minus 2x. Well, we know 3 to the 3rd is 9, or so, geez, I cannot do math, sorry. 27 equals x squared minus 2x. And then to solve a quadratic, it has to be equal to 0, so you're going to have to move this over. So I end up getting, let's see, it looks like x squared minus 2x minus 27. And this is when you would go through and factor. Now, I just made these numbers up, so they're probably not going to factor. Yeah, just looking at them, they don't factor. But let's say they did. Let's say they factored to x, I don't know, minus 9 and x plus 3. Like I said, it doesn't actually factor that, but the ones you would have on a test would actually factor. So remember, they're opposite signs, so x is 9 and negative 3. And generally it's the negative one that's not, that's going to be extraneous. Not always, but most of the time it's the negative one that's extraneous. Let's see. Okay, so like the one at the top here, those are actually one of the easier ones. If you see both sides have the same log base, in this case both log base 3, you can actually kind of ignore them because that part's the same on both sides. So then you just set these two equal to each other. So like 3x plus 1 is equal to x plus 5. And you would go through and you would, minus x to both sides. So we get 2x plus 1 equals 5. Minus 1 to both sides, so I get 2x is equal to 4, so x equals 2. Okay, so those generally come out to pretty nice numbers as well. Okay, so one like this bottom one, basically if he gives you one like this, you want to get it so that both of these bases right here have the same number. And especially if he gives you a fraction, this is probably the base number right there. Okay, so like for instance over here, I can rewrite 8 as the same thing as 2 to the third. Okay, 2 to the third is the same thing as 8, so I can rewrite that with a 2. Same thing with this one on the side. 1/2 is technically 2 to the negative 1. Okay, it moves it back up. And then once you do that, basically what happens is those bases are essentially gone. You don't need those bases that are the same, kind of like that one at the top. So this just becomes 3 times 3 to the x equals x plus 1, and you would just go through and do algebra and solve for your x. Okay, so I hope that makes sense. Okay, these, if you have a log equation, you want to do kind of that loop-de-loop thing. You want to get this to be a exponent, so you're going to start with your base, raise it to that number, equals that. So this is the same thing as 4 to the third equals x plus 1. And you would just go through and solve. I think 4 to the third, I don't have a calculator with me, I think it's 64 equals x plus 1, so this means x would equal 63. Okay, so something like that. Okay, so I try to just make up some questions kind of like the ones you were asking. Okay, so the other thing you were asking was transformations. No matter what function it is you're dealing with, whether it's a exponential, log, all kinds of different functions, pretty much anything that goes with the x. So like if I had, my original function was 3 to the x, and my new function is, 3 to the x minus 2 plus 5 or something. Any movement with your x is always the one that goes left or right, but that's always the one that's backwards of what you would think. Minus 2, you would kind of think left initially, but it actually means you go to the right. So this one goes to the right too. And anything that's added or subtracted behind it is what moves it up or down. So if it's plus, it goes up. If it's minus, it goes down. This one's going to go up too. And this same kind of thing works with your logs too. So like if I had, trying to think of like a basic log. So let's say if I had a log base 3 of x and a log base, oops, can I write? A log base 3 of x plus 1 minus 2 or something like that. Again, the one with the x is the one that goes left or right. It's just opposite of what you would think. This one actually goes to the left 2. And anything behind it means you're going to go up or down. So this means I got to go down 2. Pretty much if you have a change of sign with your x, so like if in this last one we were looking at also this changed to a negative x, anytime that you have a negative x, basically it means that you're going to go through and do a reflection across your y-axis. If you have a negative in the front of the function for your new one, it just means you reflect across your x-axis. And those are really kind of the major ones. I mean, you do have the vertical stretches. But in all honesty, what's easiest for most students is they'll plug the original one in Y1 and the new one in Y2 and just visually look at it. Did it get skinnier by stretching, or did it get wider by shrinking? A lot of students will do that too. You just kind of see their movements from them. I'm not sure exactly kind of what your question was, so I hope that helps. And you said growth and decay. I don't know, like, specifically what what you're talking about. Necessarily, if you're talking about, like, the PERT formula or, those sorts of things, I'm not quite sure. So, pretty much, if you have something that's growing, so let's say if I had an account that has, let's say like $5,500 and it's growing at a rate of 3% per year. Oh, jeez, I just wrote 38. It's been a long day. 3% per year. And you want to figure out how much it has after 10 years. Okay, so you're always going to start with your initial amount. And then if it's growth, it's going to be 1 point, and then whatever your percent is as a decimal. 3% is 0.03. Your exponent would be 10. That's a growth. Whereas like your decay, let's say I had a car that I paid $5,500 for that's depreciating at a rate of 3% per year. You want to figure out how much that car is worth in 10 years. So you still start with your initial amount. Now depreciation is a little bit different. It's actually going to be below 1, so it's going to be 0. Darn it, come on, work with me here. It's not wanting to make a point. There we go. 0 point. You basically have to do 3% or 0.03 below 1. So 0.03 below 1 is 0.97. Okay. So growth means it's going to be kind of that number above 1, whereas decay it's going to be, that decimal place below 1. And we're still having our 10 years. And I think that's kind of all the ones that you were asking for. Like I said, I'm not really sure on the growth or decay because all you had written on your sheet was growth and decay, so I don't know exactly what you're going to. So I hope that helps. I think you can do just fine. Don't let it get to you. I'm sure you'll do just fine.